Good morning, everyone. Today we're going to be doing. Oh, actually, you know what? Sorry. Today is 11:45 a.m. Saturday, July 12th. There you go. And we're going to be working on burst balloons, which is a 2D dynamic programming problem labeled as hard. Now, I read this yesterday, and I still don't know how to do this. So we'll see how this goes. I doubt it goes good. Let's see. Okay. So I'm thinking, um, I was thinking like my original idea is like we can just index through. I'm trying to think of like how to 2D this though, you know? Um, Public means 0. Okay, good to know. It's hard. It's tricky. This is a tricky problem. The fact that it could be 0 is pretty interesting. I kind of hate them for the fact that they didn't outline that as one of the example problems because that's a good example. 0 is a pretty strong edge case, depending on how some people might debate on writing their algorithm. So you have like n choices here, so you can go like 3, 1, 5, 8, right? So this will give you some sort of amount, and then it'll push you down to 1, 5, 8, and then your amount. And then you can choose here. So one of my initial thoughts is the 2D array is your amount and then the tuple. But that just like, is that correct? I just feel like that's so not right. Cause I don't know. I feel like that's gonna use way too much space. Let's see. Okay, so no, sorry, not index, amount. There you go. if if array length of array equals 0, then we return amount. The amount we make. And then I'm going to say if, this is the part, if amount and tuple of array, this is so bad, not in cache, then we do our check. So I'm going to basically go for index in array, for index element in enumerate array, say solution equals 0. Okay, I'm gonna say left equals 1, right equals 1. If index minus 1 is less than 0, then is greater than or equal to 0, sorry, then left equals array of index minus 1. If right plus 1, nope, if index plus 1 is less than the length of the current array, then right equals array of index plus 1. And then we're going to do DP. We say solution equals max of solution, and DP DP of amount plus, I'll put a little tuple here, or a little parentheses. So I just need some space to be able to read. It's getting too much, it's getting to a point. And then it's going to be array from index, and then plus array of index plus 1 onwards. And Python is actually stupid easy for this kind of problem. Well, actually, we'll see. You know, we don't know for sure. This could totally be a complete failure. Okay. And then cache of this actual ridiculousness is going to equal to solution. And then we're going to return return the cache. Okay, and then now I'm going to return DP of 0 and nums. And yeah, let's try that. See if we get anything from that. Anything of use. Okay? Amount. that's a silly error. Wow. I'm guessing it's kind of a space complexity error, though. Kind of using way too much space for this full array approach. Time limit exceeded. Time limit exceeded. Oh, okay. We're doing a little bit of an infinite loop here, huh? Okay, I'm going to start opening up some hints. Cubed. Wow. In squared space. Sheesh. Alright. Bum 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 bum. I'm a bit confused on what he's saying by this. He's talking about like splitting the array, but it's like that's not the case. When I pop this one, it doesn't mean like that now I have an array of 3 and 5, 8, yeah? Because like 3 by itself would just be 3, then that's plus 5 times 8 times 1, which is 43, when in reality it should be way bigger than 43. to be 120. So are we multiplying the two subarrays? Yeah, I'm confused as hell as to what's going on there. Bum 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 bum. Bum bum. I'm not caching properly. I don't know. I'm gonna throw in the towel on that one. I don't like the hints I'm getting. I'm just feeling like I'm not getting anything out of those hints, anything of substance. Let me think about it real quick just before I give it. Um. Ooh, shit. Okay, yeah, I'm gonna give up.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve burst balloons, and this problem has really earned that category of being a hard problem. So this is going to be another dynamic programming problem, and we're going to solve it with the optimal solution, which is going to be big O of n cubed time complexity, and I believe big O of n squared memory complexity. And I'm going to try my best to explain the intuition of this problem and kind of walk through my thought process, but if your question is, if you saw this problem for the first time in an interview, how would you be able to solve it? That's a good question, and honestly, I don't have the answer to that unless your interviewer gave you a couple of hints that kind of pointed you in the right direction, because this problem requires a couple tricks to get it to work efficiently. So the description is pretty simple. We're given n balloons indexed from position 0 to position n-1. Each balloon is painted to that balloon at that particular time. And of course, we might have a balloon that's on the boundary or on the edge of our input is obviously 8. Since we popped this one, its left neighbor now is going to be the 3 that's over here. So we're going to do 3 times 5 times 8. So after we pop the 5, we now have 2 remaining. We're going to pop the 3 first, and that's going to give us 3 times 8. And the left neighbor, of course, remember we talked about at the beginning, is implied to be a 1. So then we're going to get 1 times 3 times 8. Now the 3 has been popped. Last one left is just the 8, right? So the neighbors of that implicitly are just 1 and 1. So 8 times 1 times 1. We add that up to our total. We get 167. Now these implicit extra 1s on our input array, for example, those are not actually going to be popped, right? So we need to remember that, because obviously if we did pop them, right, we pop a 1, we'd add 1 to our total. And if we pop the other one, we'll add another 1. But that's not actually going to be the case, right? We don't want to pop these extras. So even if you can't get the dynamic programming solution, at the very least, we know that there's a brute force approach, right? We could choose to pop 3 first. We could choose to pop 1 first, we could choose to pop 5, we could choose to pop 8, right? And then we could continue down this decision tree, right? That's the brute force, right? Something like a backtracking approach. But in that case, obviously we have n choices roughly at each layer, and the height of the tree is going to be n, so basically the time complexity is going to be something like n to the power of n. Now that's not super efficient, and in this case we actually can do better, but it's not easy to arrive to that solution. So now let me explain a little bit of the thought process to get us there, and then I'm going to jump into the code. In this case, the code is actually not too bad once you see the couple of tricks that we need in this problem. So we know the brute force approach, but can we identify any subproblems? Your first idea might be something like this. Okay, so let's say I pop the 5th element, right? We pop this balloon. Now we have a new subproblem, right? We have this entire array minus this value as the subproblem, right? Or for example, maybe I popped 1. Now we would get this entire array except the 1 as a subproblem. Right now, if I continue popping, for example, I pop 1, next I pop 8, now we have a different subproblem. So if I keep going like this, how many subproblems are we going to have? Well, basically what we're doing as we pop elements, we're basically getting every single subsequence, right? Now, how many subsequences for an input array are there? Well, for each value, we can choose to include it or not include it, right? So for each value, we have 2 choices, 2 times 2 times 2, right? We're basically going to do this for the size of the input array, which is, let's say, n, so we're going to have 2 to the power of n subsequences. So basically what I'm getting at here is this is not the correct subproblem that we're looking for. We need to look for an even more simple subproblem, because if we have this...
Oh, man. That's crazy. Okay, so what's the other subproblem? I saw him listed out. He said something about I and J. It's like, I was confused. I wasn't able to understand what he meant by that. Maybe in the video it'll like make more sense.
Many subproblems, that's not going to help us. Caching something like this is not going to make the solution more efficient. We want to get something like n cubed, n squared, etc., right? This is what I'm aiming for. Let's try to see if we can get it. So let's say I pop the 5. Now, is there an even more simple subproblem? Well, we notice now we actually have 2 subarrays, right? We have 1 subarray over here and 1 subarray over here. Now, these subarrays are contiguous. They're not subsequences. That's pretty good, because we know that at most for an input array of size n, there could be at most n squared subarrays. So that's something we can work with to make an efficient solution. So now you might think, well, can I take each of these subarrays, right? Basically by popping this, we got something like 1 times 5 times 8. Now we want to know independently what each of these subarrays could get us, like how many maximum coins could this subarray and this subarray get us, right? Independently. But what we're going to notice is we can't just look at this subarray independently, right? Because independently a 3 times 1, right? The max we could get is we first pop the 1, right? In that case, we get 1 times 3, and the right neighbor is nothing. So once we pop that, and then we pop this 3, right? Then we'll get 3 times, basically just 3 by itself, right? So we pop this, then we add the second balloon that we pop, so we get a total of 6, right? Just independently if we had this subarray 3 and 1. But we know that in reality, this 3 and 1 is now going to be connected to this 8, right? And independently, what this 8 would get us is 8 by itself, right? Because it doesn't have any neighbors. So in total, if we took a look at both of these independently, we'd get something like 6 plus 8, so in total 14, right? But in reality, when we look at 3, 1, 8, what's the max we could possibly get in this case? Well, we pop the 1 first, right? Then we get 3 times 1 times 8. Now that's 24. That already by itself went over the total that we would get if we did these independently. So basically what I'm getting at is we can't break the problem up like this, right? We can't look at these arrays separately, because in reality, we know that they're going to be connected to each other. Okay, so that's not going to work. Now, this is the part where you have to be kind of clever. We said, what happens if we pop this one first and then try to do the remaining array? Let's reverse our thinking. Instead of popping this first, let's say we pop this value last. So what happens if we pop this value last? Meaning we pop this entire subarray before, right? Before we pop this, and we pop this entire subarray before we pop this. What's going to happen then? Well, we know if this is the last value that we pop, meaning we popped everything here, we popped everything here, its left and right neighbors are both going to be 1, right? There's going to be a 1 over here, and there's going to be a 1 over here. So we're going to get 1 times 5 times 1. But what's the remaining amount that we get from popping these 2 subarrays now? Because in this case, since we're popping this value last, that means these 2 subarrays are never going to be connected to each other ever, not at any point, because this is being popped last. So since these 2 subarrays are not going to be connected, that means we can now pop them independently. So let's take a look now. Let's pop this 3, 1 independently. what's going to happen? Well, we remember when we pop this independently, we're basically going to get 1 times 3 plus 3, right? That's going to total up to 6 once again, right? But that's not actually what we're looking for, because remember, this subarray is not independent. It's true, we're going to pop this before we pop the 5, but we can't just forget about the 5, right? There is a 5 right next to this 3, 1. So in reality, when I pop the 1, I'm going to get 3 times 1 times 5. And then when I pop the 3, because we know we're popping this last, right? So we are popping these two first, but then when I pop the 3, I'm going to get 1 times 3 times 5, right? Because there's an implicit 1 over here. So how can I handle that? What I'm saying is, our array hasn't actually changed. There is the 5 still over here, but we want to pop all of these elements before we pop this 5. How can I handle that? Well, it's actually not too different than what we went over at the beginning. Remember, we said that, let's say we had a single element in our input array, let's say it's a 3, right? We're assuming, even for this input array, there's going to be an implicit 1 on the left, and there's going to be an implicit 1 on the right. These two values are not going to be popped when we're popping this array, but we're still assuming that they're there for that computation that we're going to be doing. That's exactly the same rule that we're going to follow. So when we go from up here to down here, right, this is our subproblem, so we have identified what the subproblem is going to be. It's going to be this subarray. The only thing we have to remember is, just like at the beginning, how there's going to be an implicit 1 on the left, now there's going to be an implicit 5 on the right. So for the subarray that we're doing, the left boundary is going to be at this value, the right boundary is going to be at this value, but these values are not going to go away. We are going to leave this in the input array, and we are going to make sure that we have an implicit 1 at the beginning of the input array. And similarly, when we want to solve this subarray, we are going to assume that, yeah, there's just a single 8, right? So the left boundary is going to be here as well as the right boundary. Both boundaries are going to be here, but we're going to assume that there's an implicit 1 at the right, and this 5 is not going away. The 5 is going to be here as well. We're not going to pop it, because take a look at our boundary. Our boundary tells us just to pop this subarray before we end up doing anything else. So this is going to stay here. We're not going to pop it, but it is going to contribute to the total number of coins. For example, when we pop 8, we're going to get 5 times 8 times 1. That's going to be the total number of coins we get once we pop this entire subarray. So using subarrays, using this technique where for every value, we're going to identify, well, what if we popped this value last? That allows us to actually get a subproblem that we can cache. Now, in our cache, it's going to be, let's say we call it DP, this is our cache. It's going to be a two-dimensional cache, because we are going to be using the left value as the first index and the right value as the second index. These left and right values are basically just going to tell us what the subarray is from the original array, right? Left is going to be the left boundary, R is going to be the right boundary. With that being said, let me just give you a quick high-level run-through of the algorithm, and then we're going to dive in.
Okay, that is actually very interesting. That is kind of ridiculous, too, how they expect that to be solved. Okay. I will, before I listen to his last bit of comments, I'm going to try this one more time with kind of that idea of caching in mind. If I still can't do it, I'll use the help of his comments that he's about to use, and if that still doesn't work, then I'll just have to look at his code and see if I can understand it. But cache is a 2D array. I'm lazy. I'm going to do a dictionary. That's how I am. I'm a lazy guy. Definition of a DP. So I'm going to use left, or actually I'm going to go L, R, and left out. Left out and right out. Let's see if that is correct. So if left is greater than right, then return, I'm going to say none for now. I'm going to say errored. I just don't know what to do for that yet. I'm going to say the cache. If LR is not in cache, then I'm going to say for index or for index in range of L to R plus 1. Okay. Say left equals L out, right equals R out. Oh, here's the problem. I don't know what I'm multiplying. Dude, this is so tricky in the mind. Okay, this is the part where I'm gonna need his help. Not gonna lie. Yeah, I'm gonna have to watch this video. I'm a bit confused.
Into the code. So we remember in the brute force, we started out with, okay, what happens if we pop this first? What happens if we pop this first? Right? So that's going to give us a decision tree. Now we're going to do it a little bit differently. Our decision tree now is going to be, what happens if we pop this last? What happens if we pop this last? What happens if we pop this last? Which one of those paths is going to lead us to the maximum number of coins, right? So we are still going to brute force it, kind of. We are going to have that exact same decision tree. Only thing is, we're going to use a cache. We're going to take that subproblem and cache them. So for example, let's say we pop this value last. What am I going to do? And we actually are going to modify the input array. So we are going to add that implicit one at the beginning and at the end. But our boundary is going to be, left is going to be from here and right is going to be from here. That's ultimately, these are the values that we're actually going to be popping. We're not actually going to be popping these. Again, the brute force, what happens if we pop this last? If we pop this last, our left subarray becomes empty, right? There's nothing there in the left subarray, but our right subarray is going to have this entire portion, right? So since currently our left boundary is here and our right boundary is here, if we pop this value last, this is what our total is going to be. We're going to get, so if we pop this last, we know we're going to end up popping everything here before that, right? So when we pop this value, we're going to get 3 times 1 times 1, right? So what I'm going to say is 3 times nums of right, which is over here, plus 1, and nums of left, which is over here, minus 1. That's going to give us 1 once we pop this. Plus, we want the remaining number of coins that we get from popping the remaining portion of the left subarray. We see that there's nothing here, right? Remember, we're not actually popping this value. There's no other values in between, so there is no left subarray. What about the right subarray? We're going to take our left pointer, shift it by 1. That's going to put left over here. So the right subarray is going to be all of these elements, right? So you can see we're going to get that total amount computed from our DP, right? We're going to get it from our DP if that's already been computed as a subproblem. If it hasn't,
0? Dude, holy hell, this problem's confusing the hell out of me. I genuinely don't think this is going to be the answer. Sadly. I just feel like I'm missing quite a bit. Yeah. Oh, here you go. I mean, here's the one thing I'm missing. Element and R out. This is gonna be L out and element. I was like, huh? I can't do this. Array is not defined. That makes a lot of sense. Element is not defined. That also makes. Now, I'm going to define element right now. So element equals nums of index. Saluton. I'm getting all these errors, and then once I finally fix all these errors, it's gonna be like, wrong answer. God damn it. Fuck, dude. Like, what do you even do in that situation, man? I hate it. I hate it so much. Let's see if it makes it to 27. Let's see if it poops out beforehand. No way. Do I get a time limit exceeded? Okay, it poops out beforehand. Look at that. Look at that. Fuck.
Been computed, then we're just going to do that brute force depth first search, passing in these same parameters, right? L plus 1 and right. Now let's look at it for a more general case. If we were popping, let's say, a middle value as the last value, where we actually do have both a left subarray and a right subarray, what's the equation going to look like then? So we were looking at if we pop this value last. Next, we're going to look at if we pop this value last. We're also then going to look at this and this, right? That's basically the brute force, right? So basically, we're going to have an I, right? It's going to start here. It's going to run all the way through the end of the input array. But now, if we pop this last, we know that if this was popped last, we'd end up popping all of this first, and we'd pop this first. So then once we pop this, its left would be the 1, its right would be the 1, right? So that's where we're getting this from, right? R plus 1's here, left minus 1 is over here. Multiplied by the value at index I, which is 1, right? But then what's our right subarray going to be? Clearly, this is what the right subarray, remaining subarray is, right? How much did we get from doing that? Well, again, in our DP, or if it's not already computed in our DP, we're basically going to call our depth first search. Clearly, you can see that the left boundary now is I plus 1, right? Basically, we're taking this I, moving it over here. Our right boundary remains unchanged, right? This is the subarray. That's what I'm saying here. What about our left subarray over here? Well, the left boundary didn't change, but the right boundary was decremented by 1. That makes sense, right? So that's basically the idea. Now, my question is, we know why the memory complexity is big O of n squared, right? The cache is basically going to be from every single subarray, right? And it's two-dimensional, so that makes sense. I think why the memory is n squared. But why is the time complexity big O n cubed? Well, we know we're going to be breaking this problem down into subproblems of every single subarray. We know that there's n squared number of subarrays, right? So for once we have a subarray, right? Like, let's consider the entire input array was a subarray, right? We know that for every subarray, we're basically going to be iterating through every value, right? This is the first, this is the second, this is the, and so on, right? And considering if this was the last value pop. So it's basically taking the total number of subarrays, which we know is n squared, and multiplying it by another n because we're having to iterate through every single value for a given subarray. With that being said, let's jump into the code. Once you actually know these tricks, and especially once you know this formula, the algorithm is actually pretty easy with recursion. So like I mentioned, we are going to be updating the input array. We're basically going to be adding a 1 at the beginning and then adding a 1 at the end. We're also going to be having a cache. I'm going to call it DP because it's short. And then we can start with our depth first search function. So what?
You know what? Let's do that. Let's screw that silly thing I was doing. Let's do that. See this really changing much, but it's worth a shot, right? Okay, so it didn't change anything at all. It just now looks cleaner, which is not really a problem. It's fine. Not disappointed with it looking cleaner.
Let's define it. We know that we're just going to have left and right boundaries, right? So basically popping these and these. Okay, so now what are actually the base cases for this algorithm? Well, let's set it initially to 0, and now we're going to determine what is the max number of coins we could get for this pair. So remember, we're going to be iterating through every I, considering if at index I, that balloon was the last balloon we popped. So let's go through every index from left all the way to right, and let's compute the number of coins we could get from that. So we know that if this nums of I was popped last, we'd get nums of I multiplied by nums of right plus 1, multiplied by nums of left minus 1, right? And now to coins, we're going to add the additional coins that we would get from the left and right sub. Right? So we're going to be calling our depth first search function. The left boundary stays the same, and we're going to do I minus 1. And we're also going to be calling it for the right subarray, which we know we can get with I plus 1 as a left boundary, and our right boundary is going to stay the same. So
oh, crap. I'm doing the maximum. It should be both? Whoa. Okay. What? Really? Okay, I guess I wasn't thinking that through. Does that pass? It's slow. It might not pass. It passed. Alright, well, hot damn. I'm done with that one. That one was hard, I'm not gonna lie. But NeetCode had a pretty good explanation, so I appreciated that. Alright, well, it's 12:31 p.m. in the afternoon. I'm gonna go get me some barbecue. Thank you guys for watching. Whoops. Okay, thank you guys for watching, and I will see you tomorrow.